Hello, everyone. Welcome. My name is Chinonso Amadi, and I'm excited to talk to you all today about a very important topic in the world of data, which is building reliable data pipelines using SRE principles for data engineering. As we all know, the world we live in today is governed by data. Data is everything. It powers the app that we use, the recommendation engines we see today, the business decisions that organizations make today are all powered by data. I also want you to think about your favorite streaming service, maybe Netflix, Disney Plus, or even HBO. How does it know what shows you like, what shows to recommend for you, or even your car riding app, the Uber, the Bolt, and even the InDrive? How does it find the fastest route for you? How does it find the closest driver to which is to pair you with? All these are powered by reliable data pipelines. So I hope that at the end of our discussion today, you'll be able to know the fundamentals on which you can be able to build reliable data pipelines. But before we go on, I'd like to introduce you guys to who I am. Like I said, my name is Chinonso Amadi. I'm a senior infrastructure engineer at Bitnob. I have about 6 years infrastructure. It's basically around blend and I've been dabbling a lot of AI and machine learning systems. I'm a fellow at Bitrust, whereby you get trained on how to build applications on the Bitcoin network. I'm currently a facilitator there, leading the current cohort. My passion is focused on building resilient and high-performance systems. And that's what brings us to our topic today, on how we can ensure our data pipelines are reliable. What are we going to be covering today? Well, for today, we'll be looking at what data pipelines are. We'll be looking at the cost of having bad data pipelines. Then we'll see what SRE is, what are the principles from SRE that we can apply to ensure that we're able to build reliability in our data pipelines. Then we'll look at how we can design robust data pipelines. And then we'll look at observability and monitoring, what they mean, and how they can help us improve reliability in our pipelines. Then when failures happen, how do we handle such failures gracefully to an extent that they do not crash our entire data infrastructure? We also see tools that can help us achieve reliability and ensure that all these things work as expected. Then at the end of the session, we are going to have a live question and answer and some final takeaways at the end of our study this evening. So without further ado, we'd like to start with the basics. What really is a data pipeline? Well, the simplest way to which we can understand it is by comparing it to something we all can relate to today, and that's a water pipeline. You see that a water pipeline moves water from a source to where it's needed through connected pipes that are washed closely. If you are in Lagos like me, at some point we have something called a water corporation, whereby the government is able to pump water for us and then distribute it into our various homes. It's similar to how a data pipeline is. But in this sense, we're not moving water, we're actually moving data from one place to another. And in comparing our water pipeline to a data pipeline, we notice that they have some things in common. The first is that both of them need to have steady flow. The water and the data have to have a steady flow. Second, they need to have strong systems, a way by which there is no leak, there is no bad elements that are getting into the pipeline, thereby corrupting either the water or the data. Then we also see that they need to be regularly checked to avoid problems. In the case of water corporations, there's usually a standby engineer that is able to go around to check if there are illegal connections or if they are not connected properly. The same thing too happens with our data pipelines. There are engineers that maintain them to ensure that there are no problems with them. And we see that when they are well maintained, they both deliver reliable results. For us to make this even more relevant, we want to think about our favorite social media post. Sorry? Our favorite social media post, maybe Facebook or the likes. Facebook or Twitter. Hello, can you hear me? Am I still audible?
Yes, yes, we can hear you.
Okay. Our favorite social media post, Twitter in this case, we see that they're able to take all our posts, images, and even interactions, and they're able to process them inside a small data pipeline that enable us to create a personalized field. A good example is when you've interacted with someone online, maybe a finance guru, you've liked their tweets, you've checked their profile picture. When you reload your home feed, you notice that you're always going to have some finance content on those fields. The result of that is the power of data pipelines. But then what can we do to ensure that our data pipelines are reliable? Well, for us to address that, we want to first look at what is the cost of a bad data pipeline. There are two examples here that I'd like to give everyone. The first is in the case of a retail failure. A simple case study. We see that an e-commerce giant experienced catastrophic pricing error when the data pipeline corrupted the pricing data set. As a result, customers encountered wildly incorrect prices, leading to millions lost in revenue and abandoned purchases. The ripple effect is that they had the damaged inventory forecasting and severely eroded customer trust in their platform's reliability. So basically what happened was that there was a pipeline that usually updated the pricing on the e-commerce websites. But as a result, they noticed that a bad data set entered and the price for some goods were either super expensive or incredibly cheap. And as a result, some customers were able to lose credibility that, oh, this particular platform is selling more than intended, or for the fact that it is cheap doesn't mean they were still selling quality. And as a result, they stopped buying into that particular pipeline. The second was with a banking failure, right? A banking failure is noticed that there was a pipeline that caused transaction processing delays, resulting in customers seeing zero balances in their accounts. Massive panic ensued as customers feared that their money had disappeared, thereby flooding support channels and branches. The incident triggered regulatory scrutiny and a lasting reputational crisis that impacted customer acquisition for years. So customers went to bed with their account balance in place, but they woke up the next morning and they noticed that when they sent money, their money was being delayed for hours. It didn't even just stop at that. We noticed that they also noticed that their account balance was zero after sending money. Imagine you waking up to that. No doubt, you definitely want to find out what exactly happened to your money. And you want to spend a lot of time on the customer support, having them explain it, or even if it is a bank branch, you will go there and shout on their customer representative. All these examples go to demonstrate how bad data pipelines can cause a cascading failure throughout an organization. And these failures can disrupt business operations from customer experience to even strategic decision making. But then, why is it that we as engineers, we ensure that we are building reliability into our pipelines? Why does reliability matter? Picture this. Your data pipeline is handling millions of records per second, right? And suddenly you notice that the traffic has increased due to an unexpected event. If your pipeline isn't built for reliability, it will either crash or you're going to have inconsistent results in your data. So how do you design your pipeline to handle such failures? and scale dynamically, and even process data accurately, even in the event of unexpected issues. That's where the principles of site reliability engineer comes in. Sorry.
I know, so we can't see your slide. Okay, yeah, it's coming up.
Oh,
Yes, it's
you can
coming
see.
up right now.
Okay, okay. How about my face?
No, we can't.
Okay. So
Okay,
sorry about
I
that.
think it's better now.
All right. So that enters site reliability engineering. What really is site reliability engineering? Well, site reliability engineering was an approach to which Google developed in order for them to be able to maintain their different systems. They wanted a way by which they can be able to handle YouTube, their Google search engine, their Google Mail, as well as other Google infrastructure. They wanted a way by which it can be reliable and available at all times. And that's why they developed site reliability engineering. We see that these principles that Google developed went beyond just their traditional infrastructure. It also revolutionized how they were able to build and maintain resilient data pipelines. At the core of it all, SRE meant that they built reliability as a foundation for everything in their systems. For example, in the case of data engineering that we are talking about, we treat reliability as a feature rather than an afterthought. It's not something we come and address after we have built the system, but rather it is something we build into our system as we continue to grow. And the first part of it is that we prioritize data accuracy. In building our data pipelines, we want to ensure that the data that are going to pass through are always accurate at any point in time. The second principle is data completeness. We want to always ensure that our data are complete and they are delivered at a timely manner with strict SLAs to safeguard the integrity of the system. It also meant that in us building reliability into our pipeline, we tend to reduce a lot of manual labor. We tend to be strategic with what we are going to automate. If we are moving data from one point to the other, we want to be able to eliminate a lot of manual touch points. Why? Because when there are a lot of manual touch points, it makes our system prone to a lot of human errors. Imagine you having to gather reports about the number of users that have been able to sign up on. If you were to have a human do that tedious labor, there could be situations whereby you either have an under report or an over report. So in our systems, we want to ensure that automation is available to be able to ensure that that process is consistent and it's a repeatable process. The third point is to ensure that we have comprehensive observability. Why? Because comprehensive observability are crucial. When we have sophisticated monitoring, adequate metrics, and even logs, we're able to gain immediate and actionable insight into their pipeline performance and data quality. We're able to see how our pipelines are able to perform either under undue stress or on a normal performance level. Finally, we want to be proactive with our incident management. A lot of pipelines these days are reactive. The engineers operate on what is called a reactive mode, meaning that they're only able to address issues when incident occurs, rather than anticipating incident before they occur. A good way for us to understand that is in the way by which firefighters act. We notice that when the building catches fire, there is no water to quench it. A lot of people start going helter-skelter in order for them to be able to find a way by which they can quench that fire. And at once, they might call a firefighter to come and help them quench it. And those firefighters could spend days or hours on the road before they are able to come and take care of that particular situation. Thereby, by the time they have arrived there, the fire had engulfed a lot of properties. But if we are proactive in our approach, we'll put some guardrails in place to ensure that even though the firefighters are not there, the fires are not able to engulf the entire property. And those guardrails could include things like smoke detectors, right? There's a saying that there is no smoke without a fire. So a smoke detector is able to detect that a fire is about to ensue and thereby causing an alarm, or if possible, enabling something called sprinklers to be able to quench that fire. That's the approach we want to have towards our incident management. We want to ensure that we are not doing something called ad hoc troubleshooting whenever an incident happens, whereby we are trying a lot of things before we are able to find a solution to our problems. But rather, we want to create something known as run books or playbooks. What are run books or playbooks? These are tested response protocols that are able to allow us detect issues quickly, precise diagnosis, and swift remediation of failures before they cascade into business critical issues. So the run books is a set of steps that, if the advent of an incident, this is how you're going to approach the incident to ensure that the way by which you're approaching it is systematic and that you are proactive about it. You're not trying a lot of things with the hope that something sticks and address it. No, you have a precise way by which you are going to work on that particular problem. So in essence, we see that when we implement the principles of site reliability in our data pipelines, we have a toolbox that will be able to allow us to build robust and dependable data pipelines. But then, what principles can we apply in order for us to be able to build reliable data pipelines? I have 4 over here that I would like to go over. The first principle we want to implement is something called idempotency. What is idempotency? Well, to simply put, we want to ensure that we have something called safe retrials. A pipeline should be able to process the same data multiple times without causing duplicate records or inconsistencies. Meaning that in the advent by which our data is flowing through the pipeline and there's an error, the system breaks. When the system resumes and we retry the record, we want to ensure that in the advent whereby some records have been saved to wherever we want it, maybe a database or maybe an API or something, we want to ensure that that data, once it's retried, it does not create duplicate records. And why does this matter? Like we said, there is no ideal system out there. Failures are inevitable, right? We could have network timeouts, we could have pipeline crashes, or we could even have API failures where our data is extracting data from. And when this happens, we want to be able to retry failed jobs and ensure that it doesn't create duplicates or inconsistencies in our data. How do we then achieve this idempotency? Well, we want to be able to use unique transaction IDs, such as UUID or ULID, to be able to track data record. We want to be able to implement something called offset. Offset is a combination of 2 operations, insert and offset, and update rather. What it does is that if it notices that a particular record has not been created, it will create that record. But if you notice that that particular record has been created, it will simply look to update that particular record, thereby preventing duplicates. The third point is that we want to be able to have something called checkpointed states. A checkpointed state in a particular pipeline setting is if there is an error, we want to be able to save that state, the last job that run, we want to be able to save that state. And then when the system is back online, we're able to resume that state from where it left off. And a typical example would be in a payment processing pipeline, right? If a transaction isn't idempotent, whenever a user makes a particular payment, they will get debited twice for that same purchase. But when we have things like idempotency in place, we ensure that we are able to retry that payment even without duplication. That's what idempotency helps us to achieve. The second one is back pressure. What is back pressure? Back pressure simply means that we're able to release pressure within our systems. We notice that as data continue to flow within that pipeline, there's every possibility that that volume can grow. And when they grow and they tend to overwhelm our system, we do not want a situation whereby they lead to crashes or data loss. We want to be able to implement something called intelligent throttling, rate limiting. If we notice that the volume has increased and that the incoming request will overload the system, we want to be able to rate limit how much of that particular data is passing through that pipeline. And a typical way by which we can do that, we can switch from direct pulling of the data to something called buffering or queuing. with buffering or queuing, we are temporarily storing excess data somewhere and releasing it little by little until our system is able to handle that scale dynamically. Then the third point that we want to implement is we want to implement event-driven architecture in our system. We do not want to batch data little by little. Why? Because there could be tendency that delays could happen along the way. Rather, we want to implement real-time flows in our data pipelines to ensure that it is more scalable and responsive. And the ways we can do this by implementing things like Kafka, AWS SQS, and RabbitMQ for asynchronous processing. We want our system to be able to respond immediately. The minute it receives the data, it's able to process that data and send it out immediately, rather than waiting for it in batch jobs. The reason why we do this is because it will allow us to have low latency within our workflows, ensuring that our pipelines are able to go the minute they enter. The fourth and final point is partitioning, right? What is partitioning? Partitioning allows us to be able to distribute our data across multiple nodes. When we notice that our data volume has increased, we can easily break them into smaller chunks so that they can be able to be processed in parallel and efficiently. That way, it allows us to be able to have something called fault isolation. If a particular data is bad, because we've divided it into chunks, we can be able to address it efficiently. Okay, what exactly happened to this particular data? What's the problem? Was it not valid? Was it bad data? We can be able to address it. Why? Because we've been able to partition it. So what I want you to take away from this particular section is idempotency enables us to have safe retries without duplication. When we have back pressure in our system, it prevents system overload, even during traffic spikes. And implementing an event-driven architecture in our pipelines enables real-time and scalable processing. And when we partition our data, it allows us to distribute our workloads efficiently, thereby ensuring fast performance. But now that we've been able to design a reliable data pipeline, how do we ensure that it stays reliable even when it gets to production? Well, that's where we need to implement observability and monitoring. Observability and monitoring are critical. Why? Because they help us to understand the health and performance of our data pipelines. When we have effective pipeline observability, we are both strategic in the implementation and how the entire pipeline is built. And as a result, observability helps us to monitor 4 key performance metrics. The first is availability. How available is our system, our pipeline? Is it always online, or are there instances where it fails? And setting up observability in our system helps us to set up a key performance metrics as regards availability, something known as the 4 nines or the 5 nines, depending on whatever availability we want to have up there, right? When we have 99.9% as is shown in the screen, 4 nines, it means that we are saying that our pipeline will always be available for 52 minutes. Our pipeline will always be available throughout the year, and it will only allow a downtime for 52 minutes. That means throughout the year, we are only going to allow a downtime of our pipelines for 52 minutes. If we say that we want it to be 3 nines, in that case, 99.9%, we are saying that our pipeline will always be available throughout the year. However, we are making an edge case for it being down for 52 hours throughout the year. Another thing we want to look at is latency, right? How soon is our pipeline able to process certain jobs assigned to it? We can aim for something like 100 milliseconds in latency, meaning that our pipeline will process 95% of our jobs within that particular short time. Then the third important one is throughput. Throughput basically means our pipeline is able to process things for a sustained period of time without any error. In the case of throughput, we're always monitoring how much data is able to process within a particular given period. In this example, we're looking at 10 terabytes per hour. If our system is able to process 10 terabytes per hour, that's a good metric for us to want to monitor. And the last one is error rate. as we have established, no system is always ideal, is always free from error. Failures are bound to happen, right? So error rate basically means the amount of failure rates throughout the year that we're able to allow within our pipelines. If we notice that it has escaped that particular threshold, we implement something called circuit breakers to be able to bring that error rate down and address that particular error. So if our data pipeline has been failing over time, and we set an error rate of, we can only allow 0.1%, maybe out of 90 jobs that our pipeline is processing, one job has failed. Or out of 1,000 jobs, one job has failed. If you notice that we are going to allow for just 3 jobs to fail out of 1,000 jobs, that's a good error rate. But the minute we notice that it is exceeding that threshold, we can set up something known as circuit breakers that can be able to help us deal with that and send alerts to an engineer so that they can be able to address that particular error rate. Then we want to move on to something known as the key observability dimensions. In addition to the key performance metrics that we set, we want to be able to set some dimensions that will be able to help us analyze the state of our pipelines. The first one is our pipeline health. The jobs that are being processed, is it taking up more CPU or more memory than intended? We want to be able to monitor it. And a good way we can do that is to use something known as Prometheus collectors, right? Prometheus can help us monitor the state of our pipeline, CPU memory, and even disk space. We can even set an alerting threshold that if this particular pipeline exceeds 80% utilization in CPU, send an alert and have an engineer to be able to remediate it immediately. Another metric dimension we can set is our data quality. We want to be able to validate our data, both at extraction and even our loading points. We want to see that the data that is flowing inside our pipeline is exactly what we need it to flow. And in the case whereby we have something like schema changes, or maybe a particular value no longer exists, we want to be able to alert the engineers on board so that they can be able to address it. CFA workflows when quality drops below a particular threshold for immediate action. So if you notice that data passing, the failure rate is increasing. Oh, this is not properly validated. This is not properly validated. And it has dropped between the threshold that we have set. We want to alert an engineer to be able to fix that for us. And we see that each pipeline and the quality by which they perform has an impact on our businesses. So in an advance whereby we notice that there are multiple failures every time, the business needs to be able to know the impact of all these failures. It could be through dashboard reporting or whatever, for them to be able to know that as much as our pipelines are failing, it has an impact on our revenue. So that the business is aware and they can be able to make decisions as we regard that. And we see that each pipeline has something called a reliability contract, right? The reliability contract is what the engineer sets with regards to their pipeline. In as much as their pipeline is processing 1,000 jobs at a particular time, a realistic SLO that engineer can say the reliability contract is that they want this pipeline to be able to process 1,000 jobs over a sustained period of time, maybe like 30 minutes without any failure. And in a situation whereby they fail that SLO, the engineers on board are able to address it. And so, in talking about observability and monitoring, the most 3 important things that we as engineers or people looking to improve their data pipeline must monitor in 3 simple points is I want to be able to monitor our infrastructure, our pipeline, and our data quality. When we have proper observability and monitoring in place, it allows us to shift from being reactive to being proactive with our observability. In an advance whereby we have failure, there is something called MTTR, that's the mean time to recovery. What that basically means is that how long does it take for you to be able to resolve a particular issue with regards to your infrastructure? Because we are being proactive with our data pipelines, we can definitely improve our mean time to resolve if it was 2 hours before. Because we have appropriate observability and monitoring in place, we can reduce that to 12 minutes. And if we've been sending alerts anyhow before to our engineers, thereby inducing panic, because we have appropriate observability and monitoring there, we can reduce that alert by 72%. And we see that observability here isn't just about us just collecting metrics. It's also about us ensuring that in our data, we know that we have trust in our data. If our data pipelines are failing, we are the first that would know if it's failing, rather than having our users coming to tell us that, see, I'm unable to see my account balance, or the recommendation engine that you're always recommending, I don't like it. We're able to catch that at first, and we're then able to address it. But then, like we said, failure is inevitable. When failures happen, how do we ensure that they do not scatter our system, or they do not make our system go down in a way that our customers or whatever stakeholders do not benefit from it? It leads us to the next point, which is being able to handle failure gracefully. Even with the best design, even with the best architectural decisions, systems are always going to fail inevitably, right? So it is crucial for us to have strategies in place in order for us to be able to handle failures when they occur and minimize the impact they have on our users and other people, on other stakeholders. And one common technique we can implement is something known as retry with exponential backup. What does that mean? Well, it's a way by which whenever error occurs, we want to be able to retry it. However, we do not want to keep retrying in a way by which we end up overloading our system. A good example to note with this particular retry with exponential backup is in how someone calls us or how we call people. If someone calls you, if you call someone 2 missed calls and the person doesn't pick, you won't want to keep calling, unless it's a severe emergency, isn't it? You would rather want to wait and ensure you call at another time. Maybe that particular person is busy, right? So that you do not overwhelm that person or ensure that that person enters a state of panic. It's the same thing we want to do with our systems. We want to ensure that we have retry with exponential backup, something that allows us to wait longer between each retry attempt. The second one we want to implement is circuit breakers. We've mentioned them before. What will circuit breaker help us do? Well, in our electrical system, what a circuit breaker does is that once it notices that there's an abnormal flow of electric current, it's able to stop that current from entering other electrical systems in the house, thereby preventing a much larger failure from occurring. That's exactly what circuit breaker in this instance does. When we have circuit breakers in our data infrastructure, it stops cascading failure. Things like a particular component being unavailable and the data pipeline depending on it. Because there's a circuit breaker there, it's able to shut down that particular job from running and send down alerts to the appropriate engineers. It's able to fail fast when such services are down, thereby preventing a much bigger failure from happening into the system. The third one is dead letter queues, right? What are dead letter queues? Well, we notice that when we have implement a queue-based system, either in our data pipelines or whatever, there's some particular time where those messages are going to be published will no longer be available, right? So rather than having those messages drop off, we want to be able to capture those messages, keep them in the queue, and enable them for reprocessing. That's what the letter queue helps us handle in our system. When we notice that, oh, a particular system is prone to failure, or a particular component could go offline, we do not want the data that's flowing into that pipeline to go missing. We want to be able to find a way by which we can be able to preserve them and reprocess them at a much later time. Now, we've discussed about handling failures gracefully. We've discussed about observability. What then do we do whenever we face incidents? Like we've established, we do not want to be reactive. We always want to be proactive with our incidents. And that's why it is important that when incidents occur, we have well-defined response plans in place. We do not want to always give in to something called ad hoc troubleshooting, finding a particular solution until it sticks. No, we want to be able to have a structured incident response program by which we can address incidents. And one of the first and important steps that we can have is to be able to detect things early. As we've seen, when we have alerting and monitoring systems enabled in our data pipeline and infrastructure, we're able to identify issues early before they become a serious problem. The second thing we want to do is to be able to diagnose things quickly. We want to be able to use log and traces to find root cause. And that has gone that, oh, a particular job has spiked the system up to 95% CPU utilization for a period of 10 minutes. What we'll definitely do in that regard is to look at the logs to know what exactly is happening, right? And find out which particular job within that 10 minutes caused the CPU spike. And that's what logs and metrics help us do. They help us analyze to find out what exactly is happening in our pipeline. And then when we find and diagnose the issue, we want to be able to fix it fast. If it was a new job, if there was a new pipeline job that was deployed, we want to implement rollback. That is, we want to take back that particular pipeline to a point in time whereby it was stable, rather than now that it is having issues. But if it is something that it just occurred and we can send it something called an emergency patch, we want to be able to send that emergency patch quickly and fix that thing. Why? Because we've been able to see that when pipeline failures occur, it has an impact on business revenues. The final point is we want to be able to prevent future failures. A lot of people don't do this in their data pipelines. They don't do something called postmortems. Whenever an incident occurs, they just look at the incident and just leave it. That's not the attitude we want to have towards this kind of things. We want to be able to learn from past incidents. Why did this particular thing happen? What caused it to happen? So that when we see it, it allows us to be able to diagnose it and fix it very fast. And as a result, we also want to keep improving our monitoring, right? We don't just want to be okay with the small monitoring we have in place. If there are instances whereby we need additional monitoring, additional alerts, we want to be able to implement that. And if there are particular instances where we want to reduce manual labor, we want to add automation there to be able to reduce those manual labors. And fortunately, there are some interesting tools that can help us to be able to build reliable data pipelines, right? In regards to monitoring, we've established that Prometheus and Grafana are excellent tools. They are open source as well. They can help us to be able to gain insight into our pipeline health. A notable one is also Datadog. It's a full observability suite that can help us gain insights on our system. The second one is with regards to logging. The Grafana Labs team have something called Loki, which is a logging system. It's quite light and easy to install. And we have the ELK stack, those from the Elastic team. They're able to help us see what exactly is happening in our pipeline, the different logs, the different way by which our system is performing. Then with regards to our data quality, the quality of our data, to ensure that what is passing through our pipelines are what we want and what we expect, we have great tools like Great Expectation and DQ. A notable one that I've used recently is called Big Eye. Big Eye is able to help you validate your data and ensure that your data meets the quality you want. Even regards things like stale data, Big Eye is able to help you ensure that your data are not stale, but they are fresh based on how you want it. And for something to be able to orchestrate this entire workflow of your data pipelines, we have the Darling tools in the data engineering community, known as Apache Airflow. It's able to orchestrate how your data pipelines move from both the extraction source to a point whereby they are needed, either by your customers or by the businesses. We also have Darkstar, and Spotify has one known as Luigi. All these ensure that you're able to build reliable data pipelines, you're able to gain insight into them, and you're able to ensure that they perform as you expect. What have we been able to learn today? Well, we've been able to learn and we've been able to see that when we have unreliable pipelines, it can pose business risk. When we have failed pipelines, they can directly impact our revenues, our customer experience, and even the decision-making that businesses make. And that's why it's crucial that we have SRE principles imbibed into our development of our data pipelines. Why? Because they help us to be able to drive reliabilities. Things like SLOs, error budgets, and even systematic postmortems help us improve our pipeline stability. Why? It helps us to be able to hold ourselves accountable, to be able to learn from failures, and to be able to improve when necessary in our overall data infrastructure. And then we've also learned how we want to be proactive with regards to our observability and prevent failures. We want to monitor everything and anything from our infrastructure to our pipelines to our data quality so as we can be able to minimize downtime. And then we've also seen tools that can be able to allow us monitor, log things, and validate, and even orchestrate our pipeline so that we're able to build resilience and performance systems. At this point, I'd like to hear from you. and thank everyone who came to this webinar. I hope this presentation has been able to give you a solid foundation for understanding how to build reliable data pipelines.